Okay. So let me just, laws of exponents. Let me review them. So what are the rules that we have to work with? There's a few. One of them is if we have a to the s times b to the s, it's ab to the s power, right? If we have a to the s over b to the s, that's also a over b to the s power. Oops, my s became a 2 somehow. That's no good. If we have a to the s power, that raised to the t power, it's a to the st. All right? So those are kind of the big ones. But I should also mention of equal importance, if we 1 over a to the s, it's equal to a to the minus s, right? The critical idea really is that a to the minus 1 is what? That's a notation for 1 over a, right? Let's see here, what else can I tell you? So if we have 1 over a to the minus s, when we bring it upstairs, we get a to the s, right? So here I'm assuming that a and b are positive, okay? Although some of these things are true even if a is 0 and or negative, but just to be on the safe side, I'll assume they're positive for the moment. What else do we have? Well, we have the nth root of a, right? What does this mean? If this is equal to b, what's that mean? That means b to the n is equal to a, right? But we have another notation, right? Which is that the nth root of a is a to the 1 over n. Right? So just to give you names here, this is radical notation. And this is exponential notation. So if I say leave your answer in radical notation, you should use radicals. If I say leave your answer in exponential notation, you should use exponentials. But I have other ways of asking questions in here which save me the trouble of whether or not you know the difference between those words. I'll show you some of those examples today. I don't think there's any examples quite like that in your homework, but I like to give them as test questions, so I think you should see some of them in class, So one of the other things I should show you is, a little derivation, if you will. So consider. So if we have the nth root of a times the nth root of b, what's that equal to? Well, this would be a to the 1 over n, right? Times b to the 1 over n, right? See, what I can then use is I can use the first thing I wrote right up at the top. See that? So this right here, I can apply this formula in the case s is equal to 1 over n. So this is equal to ab to the 1 over n. All right? But what is that? That is, in radical notation, that's the nth root of ab. Right? So it's sometimes helpful to know the laws of exponents, but write them in radical notation, right? So like in radical notation, if we have the nth root of the kth root of a, what's that equal to? So while you're thinking about that, let me just point out that the line above what I've shown that the nth root of a times the nth root of b is the nth root of ab. What's the nth root of the kth root of a? Well, let's convert it to exponential notation. See, this is the kth root of a to the 1 over n power, right? But what is the kth root of a? It's a to the 1 over k power, right? So we have a to the 1 over k raised to the 1 over n. And how does that simplify? What is that? We do what? This is which rule of exponents do I need to use here? Well, I should use this one, right? But in this case, my s is 1 over k, and my t is 1 over n. So this is equal to a to the 1 over kn. So what I've shown is that the nth root of the kth root of a is equal to the nkth root of a. Now, maybe that seems kind of abstract to you. Let me give you a specific, sort of numerical version of this. So if I take the square root of, 128, and I take the cube root of that, right? Well, that is what is the square root by default? This is actually, there's a 2 there, right? So this is, we never write the 2, but you could, just to emphasize what's going on. This is the third root of the second root of 128. Well, that would be equal to the sixth root of 128. And if you wanted to do that in your calculator, well, I don't know, it depends on which calculator you got, but I have none with me, so I won't be able to. But what is 128 equal to? Let me think about this for a second. 128 is 2 times 64, right? Which is 2 times 2 times 32, right? Which is, what's 32? 2 times 2 times 2 times 16, right? Which is 2 times 2 times 2 times 2 times 8, which is 2 times 2 times 2 times 2. 8 is 3 2s, right? So if you count them, there are 7 2s there, right? So 128 is actually 2 to the power 7. Okay, so if I wanted to simplify that without a calculator, since I left it in my office and it's very far away, my office is so very far away I can't go get it, this would be the sixth root of 2 to the 7th, right? And so I could simplify that as follows. This is the sixth root of 2 to the 6th times the sixth root of 2. See, because 2 to the 7th is 2 to the 6th times 2, right? And what is the sixth root of 2 to the 6th? Well, it's 2 again. Okay, so what we have is 2 times the sixth root of 2. So, I mean, I don't know, just giving you a example calculation. Depending on the instructions, I might be totally fine with just the sixth root of 128 as the answer, you know. But anyway. Okay, so we have these properties of nth roots. What else can we say about nth roots? How about what is this rule here? What's star look like in the radical notation? If we have the nth root of a divided by the nth root of b, it's the nth root of a over b. That's what it looks like. All right. So, fine. And then there were two more subtle things. Well, here's a couple things that are not subtle. If I have the nth root of a raised to the nth power, I just get a again. That's true no matter what n is. Okay? So if I take the square root and I square it, I get rid of the square root. This is essentially by the definition this is essentially the definition of the nth root. But if you turn the tables here, it's a little bit more interesting. If we take the nth root of a to the n, then what happens? Remember there we had two cases. We get absolute value of a if n even, and we get a if n is odd. Okay. So these are all the rules I shared with you last class. All right? And basically the first 4 sections in Chapter 6 are just applying these rules to different problems. And there's also a rationalization thing, which we'll talk about here soon, but all right. So let's apply these rules to do some more simplifications. So let's simplify the cube root of 125 over 27. So we use, that's the cube root of 125 divided by the cube root of 27. So it's helpful to, be aware of some squares and cubes, right? Like, I'll write some up here for our future reference. 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, right? 5 squared is 25. You got those. How about the cubes, what they look like? 1 cubed is 1, 2 cubed, 8, 3 cubed, 27, 4 cubed, 64, 5 cubed, 125. So there's the first 5 squares and the first five cubes. If you have these in mind, then, if you know it, then you look at the cube root of 125, you go, oh, well, that's the cube root of 5 cubed, right? And there you've got the cube root of 3 cubed. So what are those? It's just 5 over 3. Now, this, of course, you could use your calculator to do, right? You could just plug in your calculator and hit the fraction symbol, and you'd get this, right? But there are other problems which are more symbolic, right? And you probably can't use your calculator to do these as straightforward. So here we have square root of 25 over y squared, right? So we do square root of 25 over the square root of y squared. What does that give me? Well, the square root of 25, we know that. That's 5, right? What's the square root of y squared? So your book I would say often your book assumes that like y is positive in this kind of problem. So I was basing this on example 20, number 20 on page 474 of your book. And your book puts y here. And if it does that, what's it assuming? It's assuming y is greater than 0. Like otherwise, I would have to put absolute value there because we're looking at the square root of the square, right? So anytime we have an even root of an even power, we put absolute value. So unless we know it's positive, and then we can kind of skip it. All right, one more example of this type, and then I'm going to move on. So example 3. Here we have the cube. Oh no, I already did that one. Here's a better one. So we're supposed to divide and simplify. The cube root of a squared b to the 4th divided by the square root of ab. And I'm going to break from the textbook, and I'm going to say, a way I would often ask this question, like on a test or something, is I might say, this is equal to a to the power m, or let's say p, and b to the power n. Find p and n. So what I'm saying is simplify it in this form, right? But I'm forcing it should be unambiguous what the simplification has to be. So how do we do this kind of problem? We just apply the rules that I've set forth here, guys. So I'll do it up here. I've got the cube root of a squared b to the 4th divided by the square root of ab. Okay, so there are various ways to do this kind of problem. I think a good method, one good method, is just to do everything sort of, just separate everything into pieces. So I got the cube root of a squared. I've got the cube root of b to the 4th, right? And then I've got the square root of a, square root of b. So I've just used the properties of the cube root and the square root. The cube root of a product is the product of the cube roots. The square root of a product is the product of the square roots. Then next up, I will put down what this means. This means a squared to the 1/3 power. This means b to the 4th to the 1/3 power. And we're divided by a to the 1/2 power and times b to the 1/2 power, right? One more step. Well, maybe at least one more step. This is a to the 2/3 times b to the 4/3 divided by a to the 1/2, b to the 1/2, right? Now my goal is to put it in what form? A to the power p, b to the power n, right? So what do I do? That a and b in the denominator, they got to come upstairs. What does that cost us? So a to the 2/3, b to the 4/3, those just stay there. And then we have a to the minus 1/2, b to the minus 1/2. Does that make sense? I mean, I'm following the rules that I've set at the start of class. And then what? We've got, so I think oh look, I missed a rule. What was the rule I missed? The rule I neglected to tell you at the start of class is this. If we have a to the s times a to the t, we get a to the s plus t. Right? That's kind of an important one. So here, I'm applying that principle. I multiply a to the 2/3 times a to the minus 1/2. That gives me a to the 2/3 minus 1/2. Okay? And then I have b to the 4/3 minus 1/2. All right? And I would encourage you guys, if you're good at fractions, great. If you're not, Don't be afraid to use your calculator here because, these are the kind of places where we tend to make mistakes, right? But I'll write it up here. 2/3 minus 1/2, that is 4/6 minus 3/6. So that's 1/6. And likewise, 4/3 minus 1/2, well, that's 8/6 minus 3/6, which gives us 5/6. So we have A to the 1/6, B to the 5/6. So what's the answer to the question? So you compare this to my A to the P and B to the N and read, what do we read? P equals to 1/6 and N equals to 5/6. See, this is a way I can ask you guys questions about simplification without being ambiguous. Because if you read the textbook, they give you about 4 different versions of simplification. And in the defense of the textbook, they do give words to describe the particular subkinds, like subtypes of simplification that they're after. But I really don't want to penalize students for not understanding the distinction between those 4 different types of simplification. And a way I can do that is to ask the question in this form. I can say, simplify this expression such that it's equal to this, and tell me what P and N have to be. So, does that make sense? I hope. Shall we do another? We could do another. Let's see here. I'll do another one that's a little bit different. What am I on? Example 4. So here we have the 4th root of x squared y cubed divided by the cube root of xy. All right? I'm going to tell you that that's equal to the 12th root of x to the a, y to the b. My question is for us to find a and b. All right, so we've got, I'll write it down here again, 4th root of x squared y cubed divided by the cube root of xy. So this is x to the 2/4, steps here. The 4th root of x squared, the 4th root of y cubed divided by the cube root of x times the cube root of y. Now I'm going to go over to exponential notation because, exponential notation is easier to do arithmetic in, at least to start with. So this is x to the what? X to the 2/4, y to the 3/4, divided by x to the 1/3, y to the 1/3. So since I know where I'm going, I think if I can figure out, if I can put it in the form I don't want things in the denominator, right? I just want things in the numerator, so to speak. So that's of course 1/2, right? 2/4 is 1/2. So we've got x to the 1/2 minus 1/3, y to the 3/4 minus 1/3. What's a half minus a third? It's a sixth, right? So x to the 1/6. What's 3/4 minus 1/3? Well, that's 9/12 minus 4/12. That's 5/12. So, well, what do I have? I've got x to the 1/6, right? And that's y to the 5th to the 1/12 power, right? So we've got x to the 1/6 times the 12th root of y to the 5th. So I think we can pretty much see from here that b is likely 5, right? How do I rewrite x to the 1/6 as a 12th root? 1/6 equals to blah over 12. What do I got to put for blah there? 2, right? Yeah. So I can rewrite 1/6 as 2/12, which is, of course, the 12th root of x squared times the 12th root of y to the 5th. And then, of course, this is the 12th root of x squared y to the 5th. From that, and the problem statement, I can tell you what a and b are. Looking at it, I can tell you a is equal to, well, 2, and b is equal to 5. So I would say example 4 is a bit of a challenge problem, right? Whereas example 3 is kind of like straight down the middle. Everybody should be able to do example 3. Example 4, there was this kind of tricky thing of figuring out how to make things become 12ths at the end. That's kind of a pain, you know. So admittedly, my example 4 is more complicated. All right, so we need to talk a little bit about addition and subtraction involving radicals. So this is section 6.4. So example 5, if we have 3 times the square root of 2 minus 7 times the square root of 2, what do we got? We go 3 minus 7 times the square root of 2, right? So we've got apparently minus 4 times the square root of 2. So, yeah. Example 6. Suppose I have the square root of x cubed plus the square root of x, and I want to factor something out there. Here we're going to assume x is greater than 0. So the point of the example 5 is that we have to have the same term to factor, right? To use the distributive property. So for this one, this would be what? The square root of x squared times x, right? So I could do this as the square root of x squared times the square root of x plus the square root of x. But the square root of x squared, since x is positive, is just x again, right? So square root of x cubed is x root x. Well, now we've got the same thing on both terms, right? So we can factor it out. So I can now rewrite this as x plus 1 times the square root of x, like that. So the key idea here is when we're working with radicals, we have to have them match up in order to actually like group similar terms, you know. Here's one with two different kinds of radicals, so you can kind of see what's going on. Example 7, you might have 3 times the square root of 6 minus 2 times the cube root of 7 plus the square root of 6 plus 10 cube root of 7. So if you've got something like this, you can only add the like terms, right? So this term and that term go together. We get 3 plus 1, square root of 6 from those, right? And the other terms go together. This guy and that guy go together, so we've got plus 10 minus 2 cube root of 7. So we can only add like terms is the thing, right? And I was really only able to combine these in the example 6. I was only able to make them like terms by doing this little algebra step, you know. It may or may not be possible to actually add things in this way because it may or may not be possible to make things into like terms. But anyway, this is the general principle of things. So we have 4 root 6 plus 8 times the cube root of 7. There's no way, no nice way to change square root of 6 into the cube root of 7. So, I mean, we just leave it like that. Let's see here. So I think the symbolic problems are a little bit more interesting. Let me look at another one. This is number 23 from this 6.4. Which I will call example 8. So here we go. We've got the cube root of 24x all right, cube root of 24x minus the cube root of 3x to the 4th power. All right. And we're supposed to try to factor something out of this, basically. So let's see here. I'll rewrite it this way. So we've got the cube root of 8 times the cube root of 3x. How do I do that? Because 24, right, is 3 times 8x, right? Do you guys agree? 24 is 3 times 8x, so I can break this cube root of 24x into the cube root of 8 times the cube root of 3x. And then I've also got minus the cube root of x to the power 3 times the cube root of 3x over here. So there I noticed that 3x to the 4th is really x cubed times 3x. And that gave me over here. Again, using the cube root of a product as the product of the cube roots. Now the reason I did that, you see why I did that, is because the thing that popped out at me for this problem is that there's a common, like this is the most I can get in common for both of these, this guy, right? Like that's the best common factor I can get from these two because I can only get an x from this one, right? So I'm stuck at cube root of x, that's the most I can get. And I've got a 3 in here, right? I've also got a 3 in there, but I got to peel off the 8. So what this gives me then, what's the cube root of 8? 2, thank you. So we've got 2 times the cube root of 3x. What's the cube root of x cubed? Well, that's x, very good. And so I've got cube root of 3x again. And so then I can factor. I've got 2 minus x times the cube root of 3x. There you go. Let me look at another one of these. So here we go. This is number 35 from section 6.4. So here we're faced with the square root of x cubed minus x squared plus the square root of 9x minus 9. So guess what we're going to want to do here to see things clearly? We're going to want to factor, all right? You want to do factoring in this case. Uh-oh. I think I forgot to change the camera over. Sorry, people at home. In other words, sorry, most people. Let's see here. Okay, so how can we factor this? We got what? We got the square root of x squared times x minus 1, right? And over here, we got the square root of 9 times x minus 1. Oh, look at that. Apparently, there's a common square root of x minus 1 to both of these, right? So this is the square root of x squared times the square root of x minus 1 plus the square root of 9 times the square root of x minus 1. We'll assume x is greater than 0 so that we can just get an x here. Otherwise, we'd have to have absolute value of x, right? So I get x square root of x minus 1 plus 3 times the square root of x minus 1. And what does this give me? It gives me x plus 3 times the square root of x minus 1. Ooh, well, the next bunch of problems are much easier. So, you know, in fact, this is your textbook. I don't know why your textbook has the problems out of order. Like, I'm just following the text, like picking problems out, you know, as I go. But the end problems are about multiplication, which are much easier than what we've been doing. Uh-oh. So I'll go over here. So I think the multiplication problems are you know, not nearly as troublesome. So let me put up a few of them. That was example 9, the one we just did. So this is example 10. All right, so we've got the square root of 5 times 4 minus 2 root 5. We're going to multiply that out and simplify it. Then we're going to look at example 11. It's going to be a symbolic one. We're going to look at the cube root of a times the cube root of 2a squared plus the cube root of 16a squared. We're going to multiply that out and simplify it if we can. Then we're going to go back to a plain Jane kind of numerical one here. 7 plus the square root of 5 times 7 minus the square root of 5. We'll do that one next. That was example 12. And let's see here. Example 13, go symbolic again. Square root of c plus the square root of d times the square root of c minus the square root of d. We'll see what happens there. And then example 14, we'll look at what happens when we do 2 plus the square root of 5 squared. What's that mean? All right, I'll write my solutions in red. So here we go. We've got 4 times the square root of 5 minus 2 times the square root of 5 squared, right? Because we get square root of 5 times square root of 5. But what is the square root of 5 squared? Well, it's just 5 again, right? So this gives us 4 root 5 minus 10, because 2 times 5 is 10. So, I mean, you could factor a 2 out if you wanted, but I think that's fine. All right. How about this next one? Well, we've got the cube root of a out front. I'll leave that out there, right? And then we've got the cube root of 2 times the cube root of a squared plus the cube root of 16 times the cube root of a squared, right? So notice that we can just, we've got this here and here, right? So we can rewrite this as the cube root of a times the cube root of a squared times the cube root of 2 plus the cube root of 16. What happens though? Oh, check that out. What happens when you multiply these together? What do you get? I'll make the next step blue just so you can see it a bit separated a little bit. Well, this gives us the cube root of a times a squared, right? And then this number. So what is a times a squared? Well, that's a cubed, right? What's the cube root of a cubed? A. So this simplifies to just a times the cube root of 2 plus the cube root of 16. So that's kind of neat. Let me put a dividing line between these problems here. I think I estimated an amount of space example 11 would take a little bit poorly. How do you multiply numbers like this? Well, you just basically FOIL, right? Distribute. So this is going to give us 7 times 7 plus 7 times, I'll write the 7s first. 7 square root of 5 minus 7 square root of 5 minus the square root of 5 times the square root of 5, right? So the neat thing here is that the middle terms cancel. See that? And we're just left with 49 minus, what's the square root of 5 times the square root of 5? It is 5. So we get 49 minus 5, so the answer here is 44. By the way, there's a really neat thing that's happening here. We're multiplying two things with radicals, and what are we left with? Something with no radicals, right? So apparently, there's something sneaky we can do here to get rid of radicals. This is going to be important to us in our discussion of rationalization, which is soon coming. Rationalization is like the process of getting rid of radicals, basically. This one, we get what? I'm going to write it down here because it's easier. So I got square root of c, plus square root of c, square root of d, minus square root of d, square root of c, minus the square root of d, square root of d. So again, what has happened is the cross terms, these guys and these guys, they're canceling. And root c times root c is c, right? So this gives us c minus d. There you go. How do we do example 14? You got to write out what that means, right? So, I mean, that literally means 2 plus root 5 times 2 plus root 5, which is 2 times 2 plus 2 times root 5 plus 2 times root 5 plus root 5 times root 5, right? Just FOIL it out. You have binomial times a binomial, that gives you 4 terms, 4 terms. And we should group like terms. So we can group this and this, because they're both root 5 multiples. And what's square root of 5 times square root of 5? 5, right? So this is just 5. So we've got 4 plus 5, which is 9, plus 4 square root of 5. And there you go. I personally think these are easier than the ones we were doing a little bit before, which is kind of funny because these problems are from the later part of section 6.4. So I don't know. Take from that what you will. So section 6.5 is on quote-unquote rationalizing denominators. So let's look at some examples of that. How do we rationalize denominators? All right, so here we go. Example 15. Let's do 1 over 2 minus the square root of 3. So here's how we do it. This is the trick. So we take that,